Good afternoon to all. This is for the 4022 audience. This presentation will be about how to control a DC pump, which is very important. Like for example, in many chemical process, we have, you know, uh, circulation pumps, and it is not enough to control them just starting them and shutting them off. Sometimes you want to control, like, the RPMs of the pumps, so that you can, like for example in this process, to extract the energy hitting the solar collectors. So it will go through this loop, and this is a coil heat exchanger, and that heat exchanger will impart the energy to the water on this tank, and then it will go through this circulation pump. This is what is called a kind of a closed cycle loop. It's an active one because it's using uh, the circulation pump. Again, sometimes it's not enough to turn on and off a pump. You need to do something else. Like for example, if it's an AC pump, you will control like the frequency of how this pump operates, so you can control the RPMs of that pump. More into it, let's see here. Again, it's another picture of the parameters that you will need, like for example to control the pump, like how hot is the solar collector versus how hot is the tank, and based on those two you will then do the calculation, the required calculation, to know what would be the actual flow that you need on the circulation pump, just for optimum purposes to extract heat. Sometimes you don't want to run this pump at high speed when you can do it at a lower speed, and so forth. Again, this is sort of like a closed loop type because it's using a coil, a heat exchanger type of coil, and domestic water is right at the outside of the coil. Within the coil, there's sometimes glycol. All right. This is what I call, it's the same thing. They all use a pump because they're active system, but this is what we call open loop because it's extracting the water from the tank, and then that goes right to the solar collector and then return back with the tank. All right. A little bit more into it. The pump could be DC pump, and that's actually we will subject of this presentation will be to talk about how to properly control like a DC pump. All right. So this is, again, as you can see, you don't know what is inside here, so we don't know whether it's a coil or is what we call open loop or a closed loop. In any case, you need a pump, and that's what we're talking about. Again, sometime this is a more with more instrumentation for making better decision. Like for example, they add here a mass flow meter or something that measure the flow. So with this number, you can then calculate whether the pump is doing that or not, and adjust the pump, the flow, the pump flow accordingly to some mathematical calculation. Again, you use at least two sensors, like for example, the inlet sensor and the outlet sensor that goes into the tank, and so forth. And but again, the idea is to do a little bit more than starting a pump or shutting off a pump. If the idea is only starting and shutting off the pump, and we are talking about the Arduino here, you definitely can use a relay just to do that. Very simple to start something and shutting that off. But if you want to really control, then we are that will be another subject, which is the one that we're going to be talking today. And I don't want this presentation to be long. So here we are. This is the idea. What we're going to be using is either the TIP 120, sorry for that, or the IRF 520, which is a MOSFET. Any of those scheme will work. Basically, I will concentrate on this one, more familiar. In fact, I work a lot more with MOSFET than this power transistor, although you could use this one as well for the simulation. So I will concentrate on this one. So the idea here is very simple. If you put some sort of a voltage in what we call it the gate here, the G, then it's basically you are switching on the drain gate and the source, sorry, the drain leg and the source leg. The source go right to the ground, and the drain is the one that is connected with the motor, DC motor here. Here is showing an example from almost to about 60 volts being controlled by this MOSFET. Again, you just need to put some power here at the gate, and that power comes from this pin number 3 here. And I will show you there's I would say that within the Arduino you certainly can use the analogWrite in these pins like 3, 5, 6, 10, 9, 10, 11. Certainly can use the analogWrite. What I found is that if you dedicate the Arduino to do that, to drive this pin in sort of like a pulse with modulation, you cannot do anything else, because as soon as you start to do other calculation, doing some printing, it will drive these points, I mean the pins, totally off, and you will screw up the signal to the gate, and obviously you will screw up the controlling of the motor. So I did an alternative to that, and that's what I'm going to be presenting. So again, I'm going to be doing a Tinkercad simulation. I'm going to be using the MOSFET to control the motor, and you will see what I'm talking about, that trying to use the analogWrite, you can do anything else except that, just to do that right. However, what I found is if I use any pin, and now any pin, but I set what I call the cycle time. Cycle time typically for controlling a motor 20 milliseconds, and from that 20 milliseconds, then depending of what I want, like what speed I want in the motor, then I was able to control from 0 to the 20 milliseconds on. For example, at 50%, then out of that 20 millisecond, 10 millisecond will be off, 10 millisecond on. So again, I was able to do what the analogWrite does, but better, because then the Arduino was able to do something other stuff, and it didn't mess up the cycle time. I mean, in this case, the duty cycle of the cycle time that I put I set on the Arduino for controlling the motor, which was about 20 milliseconds. Okay. So the idea of the MOSFET is right here. I mean, you have the MOSFET right here, and then you put a pulse with a duty cycle, whether it's going to be off or it's going to be from that 20 millisecond, this was the width of the on cycle versus the off, and so forth. So again, analogWrite works, but you have to dedicate the Arduino to do that. You cannot take the Arduino to do something else, because it really messed up the Arduino analogWrite. Now, if I use my scheme, which is to control with any pin the duty cycle of a given cycle time, it worked perfect. So basically, this is a presentation of the motor, and so whether this is on off. So when this is on, so power will come right through here, will come out through here, and through the MOSFET down to ground. When you shut within the off period here, the MOSFET will shut down, and you have so this is sort of like an induction, like an inductor here, sorry, and that inductor needs to be discharged, and that's why you put this flyback diode, just to ensure that you don't mess up the in this case the MOSFET. So that's how it really works. with using pulse width modulation. And this 10 kilo ohm resistor is to ensure that when you are in the off state here, there's no voltage here bothering, so it will shut down with the 10 kilo ohm resistor, period. A little bit more into it, where you put the load. There's two type of a MOSFET, N channel, P channel. I use mostly N channel. I mean, for my projects is mostly where I concentrate, using the N channel. And here is a little bit of the simulation in Tinkercad. Here's the motor I'm using. It's about I set up with 30 volts. Here is the flyback diode, and here is the MOS MOSFET, which come with Tinkercad, and here's the resistor to ground, and here's the gate. Pin 9 goes right to the gate, which is this one here. And when this gate is on, then you have the drain and the source basically tied together, sort of like you close the switch when this is on. When this is off, then this switch open, and that's the idea. I add this voltage or voltmeter to read the kind of a sort of the average voltage going through the motor, just to have a kind of a clear indication of what's happening. You know, it's good. It simulates pretty good a voltage reading, because basically this is on off. This is going on and off, you know, within 20 milliseconds, depending of what I was talking. Like for example, this is my code, very simple code. Serial, I'm using the monitor, so I put 9600 baud rate. Pin mode, pin 9 is the output right here. Pin 9. I could use any pin except 0 and 1, but the others are okay to be used. Now max 20 milliseconds, and so I start here. Analog voltage equals 0. That's where I'm gonna be reading from my pot. So I'm gonna be using my potentiometer just to set the percentage that I want this line to be on or off within the 20 milliseconds. So with the pot, I will control then the duty cycle. I do a reading. I couldn't do this if I use analogWrite. I couldn't do this. The Arduino is like fully dedicated to deal with that line, but in this setup it worked perfect. So like for example, I'm averaging. Let's say that this signal is kind of noisy and you want to average it. You want to have 100 values. So this is how you do it. Here you are having 100 values. You add them together, and then you divide by 100. I'm doing a little floating math here. Divide by 100.0, and then I print that value with the carriage return. If you do this with the analogWrite, forget it. It will not work. It will mess up heavily the analogWrite. Now, as I said, the analog voltage that I'm getting is a number between 0 and 1023. I mean, that's the ADC from the Arduino. The set point, I prefer using map, simple. So the analog voltage is a value that is between 0 and 1023, and I'm going to convert in percentage. So it's a number that is going to be converted between 0 and 100%. 100% meaning I want the motor fully on. 0, I want the motor fully off. So here's the math that will do that. Like for example, from the 20 milliseconds that I have, of that, what is the fraction that has to be off, or what is the fraction that has to be on, based on this percentage? Like for example, if I set fully on 100%, when you do this 100 minus 100, that will be 0. So the off meaning that the time will be 0 from that 20 milliseconds. The 0.5 here is to ensure that I do in this side a little bit of floating math, but at the end I end up like with an integer. So let's say that this is 0, 0 plus 0.5, it's going to be 0.5, but if this is an integer, it's going to be 0. Now, on the on, obviously, if this is 100, set point divided by 100, that would be 1 times the maximum time. The maximum time is 20, that would be 20. 20 plus 0.5, that's 20.5. But again, this is an integer on set, and that would be 20. So, like if you put the pot 100% down here, that's what will you see. You will see that the off is 0, but the on is 20 milliseconds. So it goes right here to this if onset greater than 1. Definitely, if it's greater than 1, I want to do this. The same is this one. If the offset is greater than 1, I want to shut it off. So, you know, that's how it goes. Like, for example, let's say that you got the 20, and you go here, onset greater than 1. Oh, yes, it's 20. So it will turn the pin. This pin will go high, and then it will delay by this amount of time, which is 20 milliseconds. And then it check this one out. It says, if offset now is 0. So it's 0, it will not do any of this, and we'll continue, and we'll go back, and we'll average again the analog voltage, and will repeat itself, and you can do a lot of other stuff to obviously to a certain point, because if you distract too much the Arduino from doing the motor control, then again you will lose some of that ability to properly control the motor, the DC motor, you know, by doing adjusting the duty cycle within the maximum time of the 20 milliseconds. But this is 100% better than using the analogWrite from the Arduino. All right, let's see how this works right now within the Tinkercad simulation. All right, here we are now in Tinkercad. Let's see the code once more. Here's the code. Long analog voltage. Why is long and not integers? Because I want, you know, I'm adding 100 numbers, so that's why I'm using long for that. The set point is the value between 0 and 100%, and integer onset equals 0, offset equals 0, max, and the max is the is the 20 milliseconds that I'm using. And let's run it. Let's see what happened. Oh, I have this here just for if I want to print, like for example, the on, how, you know, what fraction of the 20 millisecond is on and what fraction of the 20 millisecond is off, and so forth. But so far, I mean, what I want to do is a little bit something different. I want to, like for example, here, print that value from the pot that come from 0 to 1023 maximum. So let's run this. Start simulation, and I add an oscilloscope, which is kind of nice because this oscilloscope, let's see if I can open this a little bit more, is set at 20 milliseconds, which is exactly the maximum time that I have. So from that total time of the 20 milliseconds, I can tell how much of it is on, you know, what fraction it is. And, you know, without doing too much math, you can see that it's pretty much on the off side, because this is off, this is on by a fraction of time, very little, and then continue off during the 20 milliseconds. Let's say if I move this to the middle, you will start to see like sort of like a 50% off, 50% on within the 20 milliseconds. And the motor, it seems like it's turned faster because it has more time into being on. This is sort of like the average voltage, but not really. It's just the instrument, in this case the voltmeter, is sort of like trying to catch up with the on-off of this. But it makes sense. I mean, that's how it looks like. Let's say that I move the pot a little bit more. You can see how this chain now is most of the time on, very little amount of time of that off. I can move this more into now fully on. Eventually this, let's see, this is shut off. Let's move it a little bit further. Here we go. This spot is sometimes a pain in the neck. Well, basically now it's full, so it's on all the time, and the motor is spinning at the faster speed that it was designed for at 30 volts, and pretty much about half an amp. So I mean, I can control pretty neat, and so the Arduino can do other stuff like I couldn't do when I used the analogWrite. So let's take a look again to the code. Let's see if I can push this more this way and reduce the screen a little bit. Let's see. Let me stop here for 1 second. There we go. And let's start again. Let's go to the code, and now let's go here. You see, here's what I was printing. Trying to do this with the digital, with the analog write. I mean, both instructions, the same code. I couldn't make it to work. It was hard. So, but what I'm saying, I can adjust anything that I want, and it will work perfect. As the oscilloscope. How about if I want to do a graph? And this is kind of neat. I like this part from Tinkercad. Like for example, right now I can call this up, and now start to mess with a little bit with this guy, and you see, start to provide me sort of like a real-time graph of plotting. In this case, the analog voltage coming from a number that is between 0 and 1023. So I can adjust here. You quickly see how it jumped to the 1023 full voltage now into the motor. Can adjust to anything that I want, so I can really have a good time, you know, doing this. And the Arduino can definitely do something else, like for example averaging, averaging the analog input, just in case that the input from a signal is kind of noisy. You might want to do that. But I can control the duty cycle, or in this case the how much of the 20 millisecond will be on or off, etc., etc. Let's stop here for a second. Let's change a little bit. I can certainly change the duty cycle. Instead of 20, let's put 50, and let's see what happens. If you put 50, you want to change this as well, because that 50, that would be like that would be 5 milliseconds per step. Now you increase the time, maybe you start to see a little bit of let's see, let's take a look at it. Let's see what happens. Let's start again the simulation, and let me clear this, and let's see what happens if I get to the maximum, how fast it responds. Well, so far so good. Let's see if I move to the half of it. It looks good. It looks good. How about if I go this, just to get a good grab of the pot? Sometimes you have to increase a little bit the picture. There we go. See, adjusting pretty much to a value of 123, and so the motor is it's going full on, but then quickly shut it off. So that's what's happening, and that's why you see the voltage jumping. But it's controlling the motor at the end. I mean, you need some kind of inertia here. I mean, there's something here that spins, but when it keeps spinning, so it will not be this jumpy when there's something attached to it. So I keep adjusting. Let's say adjust this to 0. There we go. Motor stop, fully stop, and that's good. Well, this basically it. Maybe I need to show. Maybe I need to show what is the problem that I was having with the analogWrite, and that will end this presentation. Let me do that. Okay, so I'm back here, and this is the code. I'm gonna be showing the code for the same setup, but I'm gonna show the code what I have here. Very simple. When you see, I mean, I have here. I'm reading the pot. I'm not doing any averaging. I'm reading one number, and I use that number, and then do the translation from 0 to 255 because I'm gonna be using the analogWrite pin 9. So I use that number. I have to delay at least 10 milliseconds just to do something else, because the way the analogWrite works is that it takes about 10 milliseconds, and you will see in a second what the setting that I have on this guy is. 1 millisecond per division. There's 10 divisions, that's 10 milliseconds. And you will see that the analogWrite typically is about, it will fire about 5 times within 10 milliseconds. Will that be about 500 hertz, which is what the literature for the Arduino said, that at least the digital pin, the 9, will work about, I would say it's about 500 hertz, if I got that right. I can check that, certainly check that. What's the frequency of pin 9? Let me do that now. Let's see what's the frequency of pin 9. Okay, according to Arduino, the analogWrite Uno, Nano, and Mini, pin 3, 5, 6, 9, 10, 11 can do pulse with modulation, but pin 5 and 6 can do up to about 980. But so meaning that pin 9 would be 490. So about 500 hertz, that will do. So let me go back to Tinkercad. I'm right here. So let's see how this works. Like, for example, if I don't put this delay here, I will mess up very quickly the analogWrite, this analogWrite right here. Let's start the simulation with it, and I can fully control, pretty neat. You can see at least 1, 2, 3, 4, 5, as I told you, like for a frequency of 500. I can go to a little bit smaller on the duty cycle, pretty much off all the time. This is the part off, this is on. 1, 2, 3, 4, 5 fighting. That meaning, again, the 500. So I can keep going down. Let's see, put a very small value here, pretty much 0, and pretty much gone. So I can go the other way, at the 100%, you get the full value right here. Now, here's where this becomes very interesting. Let's stop the simulation here, and let's, comment this line. I comment that 10 milliseconds, start simulation. All right, so no problem there, under 100%. So if I go to half of it, you see, it's pretty much stay on. So I'm messing up a little bit the analogWrite. So it's not working, stop working the way it should. Let's say if I go a little bit even more, if I can get the plot right here. See how weird the oscilloscope looks like. Extremely weird. You cannot tell what's going on. I pretty much shut it off, and that part works, I would say, but still kind of weird. Anything in the middle is just totally gone. I mean, lose total control of the motor uh, by using the analog write. So let's stop here. Let's put the delay back and see what a big difference it will. See, now it's working. Everything's the way it should. The problem with that is that you have to dedicate your Arduino to do this control. You cannot do anything else. Let's stop here and let's get the comment out here for just I want to print something. I'll put the delay. I want to print something and let's see what happened. Start simulation. And you see, you start to see this kind of weird stuff on the oscilloscope. And let's see if I'm printing. Yeah, I'm printing, but I totally lost control. You see what I was saying? I don't have any control whatsoever. Even at less than half at the pot, and I'm still seeing a very high voltage. It's like it's not following, and you can see how messy now my oscilloscope looks like. So as I was saying, I'd rather do the controlling myself instead of using the analog write. It worked perfect. This really is not the way to go. It really get messed up. I mean, even averaging, you start to, sometimes you want to average this input from this analog read from A0. You cannot do that either because, as you can see, everything got really messed up. All right. So let's stop here. Let's stop here. I think that more than enough on this subject. So again, the better approach to do this motor control for a DC motor control is just instead of using the analog write, I'd rather use my own duty cycle and based on my cycle time, whatever cycle time you want to test, for example, 100 millisecond and so forth. But the nice thing about you controlling yourself, the duty cycle, is that your code can do a lot of other stuff which are very important, and controlling the motor is just one part of it, not the 100% of it. All right, that's it. Have a great afternoon. Thank you for listening. Bye.